Hi. How are y'all doing? It is a beautiful day out. It is April 3rd, 2019, and the sun is shining. I don't know, I think it's supposed to be 50 degrees today, something like that, which is nice. Hopefully, spring will be here to stay. I'm wearing a t-shirt. Wow, doesn't get any better. So, let's start with Unit 4 to Lesson 5. We're going to talk about applications of exponential functions. More specifically, that investment things that have compound interest involved in them. Money. Yeah, that's for you. Look up that song. It's a good song. Never mind. Let's just get going. First off, before we really get rolling to this, you're going to see the number E. That's right. I said it. The number E makes an appearance in this lesson. Okay, why is that important? Because the natural base exponential function have base E. What does that mean? You know natural log? If I say the natural log of, I don't know, E, this base right here by default is E. Okay, so anytime we do something like that, that base is E. Some important things to know about natural log and E. If I take the natural log of E to the third, let's say, these cancel and it just becomes 3. Likewise, if I have the ln of 3, okay, I can really apply my ln as an exponent and it becomes 3. They really frown upon doing this, but it works mathematically. But the big thing here is these types of functions that involve E are useful for describing continuous growth and decay. All right. So if I want money and I find interest that gets continuously applied, I'm going to use E. Don't worry, there's formulas. You're not going to have to like come up with something on your own for now, I think. Let's move forward. Exponential growth and decay models involving compound interests. I almost didn't want to do this lesson, but it involves money. And I think that people need to be exposed to it. And online, on social media, everywhere, there's people that say math should be taken out and we should give basic finance math. Well, there is a math class called finance that you can take. All right, number one. Number two, this pertains to it. So let's see how many people will get good at it because it's relevant to what might be part of their future. Smiley face, wink, wink. All right, so we have growth. Growth is represented by the following equation, and we touched on this. At the end of Unit 4, Lesson 4, I gave you one problem that dealt with this, okay? I take my initial amount A. Oh, I get to use highlighters. Oh, that's a crayon. Highlighter. A is my initial amount. Yep, and again, the board is off by about 2 inches. Oh, what's funny is I just calibrated it right before I started this lesson. Okay, and you notice even for decay, we always start with our initial amount out in front of parentheses. My R, which is in both equations right here, is my rate, but that, okay, that is off by 2 inches. Oh, I'm going to recalibrate this. I'm going to start this over, and then I will throw a chair through the smartboard. So stay tuned. It's going to get exciting. Give me a second. Okay, let's. What seemed like a second to you was about 2-3 minutes for me, but I'm a time lord. So here we go. Let's start over. For growth, okay? For growth and for decay, all right? You'll notice that they both start with this small letter A here, and that is my initial amount that I'm investing, all right? It always is. You will notice that there is 1 plus or minus this R, okay, over N. The R is my rate, but we want that in decimal form. A lot of the times, they're going to give us rate in percent. We need to convert it to decimal, okay? And this fraction, the denominator is an N, okay? N is the number of compounds per year. Okay, that's in both equations. And number of compounds per year would be Well, if it's monthly, that's 12 times a year, so n would be 12. If it's weekly, there are 52 weeks in a year, so my n would be 52. We'll go over that right after this. All right, and last but not least, it is raised. Oh, my n also makes a second appearance in the exponent. I multiply it times time. Okay, that's the t variable. That's the time, number of time periods. Typically, it's in years when we're talking about investments. Okay, so both of these equations, you'll notice, are the exact same. All right, the one thing that's different is if it's growth, we're going to add to our money. If it's decay, we are going to take away. That means we're losing money. Okay, and it doesn't have to also be money. It could be population, any sort of model that represents growth or decay. All right, now the number e, which by the way is irrational, like pi. You know how pi goes on forever, 3.1415926, etc., etc., etc. E is actually 2.718, etc., etc. It's irrational. If something gets compounded continuously, that's not monthly, annually, weekly, continuously getting compounded, I use this equation right here. P is my principal amount. That's pretty much like the A. I don't know why they changed it to a P. Okay. R is still my rate in decimal, and T is still my time. I say APERT. A equals P-E-R-T. Please keep in mind, this E is a number. Okay? In the calculator, you can put E, and it will calculate it as a number. You are not trying to find a number to put in for E. E is not a variable. E is a number. So the P, that's the same thing as like our A, our rate, our time. Those are the three variables you need to put numbers in for. E is a number. E is approximately 2.718. In your calculator, don't use 2.718. Actually use the number E, which is in the calculator. We will get there. Okay? So let's apply some of this knowledge. All right, so let's fill in this table here. If you put $1,000 in a college savings account for 5 years, and the account has an annual interest rate of 6%, and it is compounded n times per year. Okay, so that means we're going to take this situation and use the exact same amounts. And by that, I mean we are going to use always 1,000 as our A, our initial investment. We are always going to use 5 for our time. And you, wow, that was interesting. Okay, 5 for our time, the T. We are going to use 6% as our rate. Of course, we need to change that to a decimal, which is 0.06. The only thing that's going to change for all of these, okay, because we're going to do it annually, semi-annually, quarterly, the only thing that will change will be our n value. And that's going to change depending on what they tell us it is for this situation. And we're going to do it for this situation where the n will change. Then we're going to do it for this situation. What do I mean? N is the number of times your money and interest gets compounded per year. If it's annually, well, annually is 1 time per year. So my n is 1. If it's semi-annually, that's twice a year. So my n would be 2 in this situation. I would still use my A, my T, and my R. Those will not change. If it's quarterly, well, that's 4 times a year, and so forth. So we're going to fill this whole table out, okay? So my formula for annually, let's start with this one. Number 1, annually. My formula for all these is going to be my final amount is going to equal my initial investment, 1 plus R divided by N, all raised to the N times T. Okay, I'm going to use that for this equation. That formula is going to be used for that whole column. Every time my A, is $1,000. That's what I'm starting with. It's 1 plus, my rate should be decimal. We don't have percent in the calculator, so we need to make it decimal. My rate is 0.06. 0.06 over n. In this case, annually, n is 1. Raised to the n times t. That's 1 times my time, which is 5 years. I'm going to put that in the calculator. And then you're going to see that everything that I got to put in the calculator after that is going to be real easy. So let me clear out this calculus. Let me do 1,000 times, and I'm going to put it in just like it's written. I'm going to let the calculator do all the work. 0.06 is my rate over 1 times the exponent of 1 times 5. And I hit enter. And at the end of that 1 year, or at the end of that 5 years, I'm sorry, we would have $1,338.23. Please, that 2 should get rounded to a 3 because the number after it is 5 or bigger. So it's $1,338.23. After 5 years, that's how much you would have if your interest was compounded annually. Now let's do the same thing, but compound it semi-annually, okay? Let's take a look. I'll do this in purple at the second one. The only thing that's changing is my n value. I still have 1,000. Still 1 plus 0.06, but now my n value is 2, raised to the n times time. All right? And the beautiful thing in the calculator is if I go up here, all right, and I'm going to change my n value from 1 to 2. And I hit enter. And I should get 1343.92. So I'm going to get 1343.92. Now, that makes sense. If I have the same interest rate, the same time, 5, the same initial investment, but my interest gets applied twice, not just once, yeah, I should get more money. My interest I'm getting twice a year, not once a year. So I should get more money. So let's go through this table. Okay, what I'm going to do is let's figure out the ends for all of these. Okay, if it's monthly, my n is 12 because it's 12 times a year. If it's weekly, my n would be 52 because there are 52 weeks in a year. If it's daily, n is 365. What about leap year? Just it's 365. Okay, if it is continuously, I am not using an n anymore. I'm using my equation, a pert, the number e. All right? So what I'm going to do is I'm going to pause this, and then I'm going to fill in all this information. I'm not going to have you watch me do it. So you should try and finish these off, and I will just show you the answers right now. Okay? Give me 1 second, and I'll show that to you right now. Bam. Bam, bam, there you go. So for quarterly, and hopefully you got these right, for quarterly where n is 4, I put my 4s in, and I should get $1,346.86. For monthly, my 12 goes in. It's the only thing that changes. I should get $1,348.85. And yes, the money will go up. You might say that's not a lot, Visca. Well, it's only $1,000. If you had 10,000, 12,000, that money will add up. Then year after year, you're getting interest on more money, and it helps. The more money you have, the more money you can make on interest. And every little bit helps, especially over the years of your life. It really does. Okay? Weekly, 52. 1349.63. Daily, 365. Okay, so we make that 365. We get 1349.83. And lastly, I don't have this one down because I want to show this to you. All right, APERT. I still have my $1,000 for my initial investment. This is a number E. My rate times time. My rate 0.06. My time is still 5. I wanted to show this one to you in the calculator. Let's clear this. Let's do that. And I'm going to say my principal is 1,000. Now, the number E appears in two spots in the calculator, both in blue. If I want to put the number E without an exponent, it's above the division sign here in blue. So I can hit second E. Then I need to put the exponent up and type it in. Okay? Or it appears above the natural log. It's not just E, it's E to the X. If I do that, that will assume I'm putting an exponent in, and I won't have to hit the exponent button. It will do that. So you can put E in with an exponent, or you can put E in without an exponent. It doesn't matter. In this case, it's 0.06 times 5, which is our time. Okay. Both of these E's represent the same thing. If I would have used the E without the exponent, I could have just hit the exponent key and put it in. And we should get more than 1349.83. And we get 1349.86. Ooh, 3 more cents. It's a dollar sign. That's 1349.86. Woo! That was a lot for a table. But you know what? That is a great visual. And we see that as the number of compounds increase. So as my N value goes up, if my interest gets applied more often during the year, I'm going to make more money. Show me a person who says, I don't want more money. If we're not doing anything, putting your money in a bank, you don't have to do any work except let your money sit there. So let me say this one more time. I don't know anybody who would sit there and do nothing and say, you know what, I don't want more money for doing no work. Come on now. You kidding me? If I got paid the money I get paid to sit at home instead of being here, you think I'd be in here? I would do my videos from home. I love teaching. I would still do it. Maybe for less. But then it would give me the ability to walk out anytime I wanted to. Be like, you know what? I'm done. See ya. And not come back because I can get paid for doing nothing. But let's forget about my fantasies and move on with the notes. Okay, example 1. A total of $12,000 is invested at an annual percentage rate of 9%. Find the balance in the account if it is compounded annually, or if it is compounded monthly for 5 years, or compounded continuously. All right, well, let's figure out our variables. This will always be our A, our initial investment. Rate, we need it in decimal, 0.09. Time is always going to be 5. All we need to do is figure out the different amounts for the different number of times it's compounded, our different N value. Annually, N is 1. Monthly, N is 12. And continuously, oh my lord, A per. All right? So if you want to pause this and do it, I'm just going to go rip through these quickly. All right. So according to my equation, I take my initial value, 1 plus my rate, which is 0.09, over my N value, all raised to N times T. Let's put that in the calculator and see what we get. 12,000. 1 plus the fraction, 0.09, which is our rate, over our N value, which is 1, raised to 1 times time, which is 5. And that gives us $18,463.49. That will round up. There's our answer. I'm being lazy. It's right there in front of you. $18,463.49. Everything for part B is the same except my N value. So if I go here, the only thing that's going to change is the 1. It is now monthly. So I'm going to make that 12. I'm going to say 1. Then I'm going to insert a 2, 12. And I'm going to do the same thing down here. 1, and I'm going to put a 2. That should be more than it is. Okay, it's 12 times a year instead of once a year. Now, so we have $18,788.17. That will not round up. There you go. Now, last but not least, the ever lovely APERT. Okay, I'm going to use the same values except continuously. So 12,000 is my initial amount, which is like the P, the principal. E to my rate, which is 0.09, times my time, which is 5. We'll do this in the calculator. 12,000. E, bam, with the exponent. 0.09 times 5. 18,800. That is even more because my interest is compounded continuously, which is more than monthly. It is continuously being applied. So $18,819.75. The number after it is 5 or bigger, so I'm going to round up. Now, the $1 million question is this. Well, Visca, if I go to one bank and they say my interest is compounded annually, and I go to another bank and it's compounded monthly, why don't I just put my money in the bank where it's compounded monthly? Because what banks do is this. Annually might give you a higher percent, 3%. Monthly might give you 2%. So they do balance out. One might be slightly more than the other, okay? They might not give you as much interest because they're applying it 12 times. Here, they might give you more interest because it's only being applied once. So you really need to do your homework when it comes to things like this, okay? More money, more money, more money. Problem 2, Jose invests $500 at an interest rate of 10%, which, by the way, banks never give 9 and 10% anymore. But this is just a math problem, and so we're just throwing that in there. Okay, Jose invests $500 at an interest rate of 10% compounded quarterly for 5 years. Maria invests $500 at an interest rate of 10% compounded continuously for 5 years. Okay, so what's the one difference? Compounded quarterly versus compounded continuously. Okay, assuming that the money will be untouched for 5 years, meaning we're not taking anything out, we're going to leave it in there and let that money build. Okay, A says, who ends up with more money at the end of 5 years? I can tell you right now, if the interest rate is the same and the money you're putting in is the same and the time is the same, the person who gets their interest compounded more should have more. I'm putting my money on Maria, no pun intended. All right, so let's figure this out. Let's figure out Jose and Maria. Jose will do in red. That is $500. 1 plus my rate, which is 10%, but we need that decimal, 0.10, over my n. Quarterly means n is 4, okay? All raised to n times time, which would be 5 years. That's not 4.5, that's 4 times 5. Maria, which we'll do in blue, Maria, 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 here we go. Continuously is APERT. So her initial investment is still $500, E. The rate is still 10%, and the time is still 5 years. So let's figure out what each person gets. Okay, so I could have answered this question logically by saying, with everything being the same, since Maria's interest is compounded more frequently, she will make more. But in a math test, if they tell you to justify your answer, this math work that we're doing is the justification. So let's take 500 times 1 plus the fraction. And no, go to, okay, the fraction. There it is. 0.10 over 4. That is continuous. N is 4. That's quarterly for Jose. Raise the 4 times 5. Okay. Oh, look at that. I put 50 instead of 500. So let me just go back there and put the 500 in. Let me just add a 0. Love it. Come on. 5, 0, and let's insert another 0. Bam. And really the decimal just moved over. $819.31. That's going to be yep, bang. $819.31. Maria, 500. E, again, that 0. Sticky, raise the point 10 times 5. $824.36. Okay, so what we're going to do, and if you want to write this, and you should, obviously you don't have the ability to slide your calculator screen on your paper. $819.31, $824.36. Okay, so we need to answer the question. Who ends up with more money? Maria. What we did here is justification. Okay, I mean, if we circle this or whatever, yeah, I guess that might be the answer, whatever. But make sure you answer the question. Who ends up with more? Maria ends up with more. Justification. Now, by how much more money did the winner's total exceed the others? So how much more money does Maria have? Well, we'll take her amount, $824.36, and we'll subtract Jose's amount, $31.05, 19. Oh my God, it's $5.05. But you know what I always like to do, even though I'm pretty certain I'm right, but you never know. I like to check that in a calculator. I take my 819.36 and I subtract my, oh yeah, I'll be okay. It's 824. So even the calculator can be wrong if the person who uses it is a dummy, like me. 819.31. $5.05. Good. That was a good question. Good, healthy question. My brain feels better. 3 is a great question. I love 3. Why do I love 3? How I love thee, let me count thy ways. Given an investment modeled by A equals 1,500 times the sum of 1 plus 0.035 over 12 raised to the 12t. Which of the following statements are true? Circle all that apply. Okay? The investment is compounded every 12 years. I see what they did there. That's false. But you might say, Visca, my N value is 12, so it is compounded 12 times. That's 12 times in 1 year, not every 12 years. Okay? 12 times in 1 year. That's monthly, not every. So this is false. Okay? The investment is compounded 12 times per year. Yes, because it's monthly. That's the right one. Ding, 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 ding. But it says circle all that applies, so there might be some more. The interest rate is 35%. My R is 0.035. If I want that in percent, I slide the decimal over. That's 3.5%. That is not 35%. No. D says the interest rate is 3.5%. True. The initial investment is $1,500. That is our A value. And that is $1,500. That is true. Boom. A represents the amount accrued, and A represents the principal. They're talking about this. That is not the principal. The principal is your initial amount. So it is not the principal. It is the amount you accrue over said time. You are good to go. Okay, last, but certainly not least for today, anyways, we will go over example number 4. And again, what a good example. Number 4 states that Emily wants to buy a car for $12,000, but does not have enough money to pay for it all at once. She goes to the bank to get a loan instead. Compute the future value of her loan if she finances her car at 4 years at 2.87% without accounting for monthly payments. Meaning, how much will she end up eventually paying back? Okay, so 12,000 for 4 years, that is going to grow at 2.87%. All right? If we are not accounting for monthly payments, I think this is just that 2.87% is going to be annually. That is an annual interest rate. Okay, so annually means my N would be 1. That's why we put this in here. We're not accounting for monthly payments, whatever. So let me just state that clearly. All right. So A times 1 plus R over N NT. That's going to be the final amount. Okay. So she's borrowing $12,000. Okay. 1 plus my rate. Okay. Now I'm glad this came up. 2.87%. If it's in decimal form, there's a decimal there. Okay, why don't we consider this? I want it in a form without the percent sign, meaning I still have to slide that over twice. Okay, 0.0287. All over, that is going to be applied once a year. Okay, my N value times time. She is taking this money out for 4 years. Let's figure out what that is. All right, put that in the calculator. And again, we're going to start this bad boy. And it is 12,000 times 1 plus, I'm going to put a fraction there. I love the fraction function. And that is 0.0287 over 1 raised to the 1 times 4. Everything looks right. Let's do this. That is 13,000. Okay, $13,438.05. This will round to a 5 because the number after it is 5 or bigger. That is what she would end up paying back at the end of 4 years. That's what her loan is worth. You take out 12,000, you're going to have to pay back $13,438.05. Okay, that's how loans work. If you're going to borrow money, you got to pay back slightly more because you borrowed it. All right. And they're saying, how much will she pay in interest? So if I take my $13,438.05, the interest is what makes it more than the original amount. So let's subtract our 12,000. She's going to pay $1,438.05 in interest. Okay? This is what the money was without the interest borrowing. This is what the money is with the interest when you borrow it. So what's that difference? What represents the interest? $1,438.05. What I love doing in pre-calculus, and I've kind of shied away from doing this. I've kind of focused more on preparing for calculus than actually learning like pre-calc content. I like doing mortgages for homes. Because if you're going to borrow $150,000 and pay it back in like 30 years, you might pay back $225,000 or $250,000. You might end up paying back like another $80,000 or $100,000 more than you borrowed over the course of 30 years. And it adds up, and I don't think people realize that. That's what finance is all about. Okay? Now, I think we're going to stop here because right now I believe we are done with money, and we are going to go right into just growth and decay with exponential models that don't involve money, like it might be population or whatever, bacteria, whatever. So we are going to stop with our last problem here with that, this poor Emily going to be out an extra 1,340, yeah, I'll be okay. $1,438. There it is. There I am. All right, and I will see you for part 2 for Unit 4, Lesson 5. Stay cool, people. Stay cool. And save your money, for God's sakes.